So good evening, everyone, and good morning. Welcome to this 57th Cree talk. Today's talk is going to be on semiconductor manufacturing in India. We have the pleasure of listening to Dr. H.S. Jattana. He's done his graduation from BITS Pilani and then worked with Rockwell Semiconductors for about 15 years. And after that, he has moved to SCL in Chandigarh, where he was deeply involved with a lot of space-related applications, which they have done for ISRO, the launch vehicle-related semiconductor applications, which he was involved in. And he's recently retired, and also is an adjunct faculty with some of the institutions like Dhirubhai Ambani University, then I think IIIT UNA, and he's also one of the mentors for IIIT UNA as part of the CBDE program. So with this brief introduction, let me invite Dr. Jattana to share his experience and perspective on semiconductor manufacturing in India, and also provide the historical as well as the future directions in this domain, with some possibly experiences coming from the space applications and so on. Over to you, sir.
Thank you, sir. So I will start with this. This is my topic, as sir has explained. And is this visible now?
Yeah.
So this is So this is. I will start with a brief introduction about the semiconductor technology and the markets, and then what is the status worldwide, and then where we are, what we are doing, and our future plans, and related to education, like how our various educational institutions, academia particularly, in electronics education, how they can contribute in this particular area. So this is a slide which shows like we talk a lot about semiconductor ecosystem or semiconductor verticals. You see, semiconductor is a very, you can say, broad wide industry. If we talk about the total market, it will be close to some $1,400 billion. So it's highly segmented, and it has a very, very high efficacy to all other industries. So everywhere you will find those tiny chips, like for sports, entertainment, or high tech, or wherever. So everywhere these chips are used. So now there are companies which we call it IDM, integrated device manufacturers, like Intel. They do everything. They will design their product, they have the design, they have the fab, they have the test, they have the packaging, and all end to end, they will do that. That's how we call it integrated device manufacturers. Then there are foundries or fabs. They will not do the design. They will only fabricate the design, and they will give you the wafer. They will not package or test. And these are the few of the companies who are what we call it a foundry, like TSMC, Samsung. Intel is also a foundry. Then there are companies who will make wafer fab equipment, WFE they are known as, and that also they are having close to $200 billion kind of the market. And the leaders are ASML, Applied, Lam, Tokyo Electron, KLA. So all these are American, Japanese companies mostly. ASML is Netherlands, and one particular equipment, which is a lithography. So they are the experts in that, and they only are able to provide extremely ultraviolet EUV litho tools, which are used in low geometry applications. Then there are a lot of other companies who are what we call it, like for a design you need EDA tools. So there are companies who will provide EDA tools. Then there are companies who will give the IPs. Like now the design is quite becoming complex, and it contains various sub-blocks. Some of these blocks can be procured as an IP, and there are like many companies who are involved in this IP business. I think total IP market will be close to around more than 10 to 12 billion dollar. Maximum of this is the component which is around last year turnover was $620 billion. So this is the component, the cost of the ICs, all types of ICs. So these, and then there are a lot of companies who are making gases and chemicals for the fab. And there are players who are doing assembly equipment, testing equipment, and things like that. So in the entire gambit, it will be close to 1,200, 1,300 billion US dollar worldwide. Now, how we are responding to the fourth industrial revolution? Basically, it's a merger of these three: physical, digital, and biological spaces. The microelectronics, the semiconductor, is helping in this. And a very good example is the watch, digital watch, which we all use. So it has all these three contents. Like it can measure your biological functions also. It's based on the digital electronics, and it can record your physical activity also. So there are products which comes because of merger of these three, you can say, spaces which were earlier not connected. Now, this industry, what is the heartbeat? The Moore law is the heartbeat of the industry. Golden Moore, as you know, he was the founder of Intel, and he had predicted way back in 1963 or 64 that the number of transistors in a chip, it will increase it will double every 24 months. He predicted this in 1964, 65 kind of thing. And this CMOS evolution started, if you see, the first batch came in 77, 78 or 80s, you can take, with 5 micron structures. And in the last, you can say now, 44, 45 years, this thing has happened. And this is the graph which shows that how the number starting from 1970, where initially ICs were they had only very few components, 5 components, 10 components. And the first IC which was made by TI and Bell Labs, it has around 12 components only. And so from 1980, it rose to close to 100 and 1,000 components. And now the latest processor which is used in the Apple iPhone, it has more than 10 billion transistor in one chip, in one silicon, in one chip. And the size of that chip may be around 15 by 15 square, which is 225 square area, having 10 billion components. So this is, and more number of transistor means we can add more functionality into that. And what drove the semiconductor industry? That is the inverse Moore law, and which means that the cost of implementing any functionality will become half. Rather, it becomes half every 1.5 year. And as is very evident, like a military flight simulator, it was costing a few dollars in 1980s. Now it has become a computer game. It is around $200, $300. This is because of this semiconductor chips which are used in those in these type of devices. What are the pillars of semiconductor innovation? These are the 4 main pillars. I will talk with manufacturing technology. We have machines. As I told, there are 5-6 companies who are involved in making wafer fab equipment. We call it WFE. So they are able to make equipment where we can do very precise. We can print 5 nanometer lines, 5 nanometer width, 5 nanometer pitch. We can make such fine structures. So those with very accuracy, very good repeatability. So those kind of equipments, and we can etch the films, we can deposit the films. And these kind of equipments have been made, which are very precise, though very sophisticated, but it is possible. So one is the manufacturing technology and is the material science. You see, when in 1980, when we started with 5 micron CMOS, there were only 20-25 elements which on the periodic table which were used in making ICs. On a periodic table, there may be 120 or elements, but now more than 60% of these elements are used in making these latest chips, which are at a very low geometry kind of structures. So material science is also playing a very you can say, important role in the in the design and fabrication of semiconductor devices. And then of course comes the design, integrated circuit design. So the design have become very, very complex, starting with a very simple designs. Now we have, you can say, multi-core processors. We are putting a lot of memory, we are putting processor, we are putting analog, we are putting camera, we are putting RF in the same chip. So the design has become very, very complicated because the transistor size has reduced. So the designer has an option of putting so many devices, so many transistor in a particular given area, but the complexity increases. And there are EDA tools which can handle, which can simulate these kind of design to test their functionality and other specifications. And packaging is another, for in the last 9-10 years, packaging has become very, very important. And we started with a 2D packaging, then 2.5D, 3D, and 4D. Now 3D and 4D packaging is quite common. And packaging, a lot of work is being done in the at present, and in the future also. It's a very important pillar of this semiconductor innovation. Another thing is the customer, which the consumer, which want to be connected anywhere, anytime. This is what gives the oxygen to the industry. So the industry has to keep on inventing products which are high resolution. The quality you might have observed, the quality of our screens of the mobile phone, the displays of the mobile phone, of the laptop, the resolution, and the speed by which you can play an audio, or you can play a video, you can transfer the video, because there are basically chips, modems, and other switches, RF switches, which are involved in these things. So the demand of the consumer is also very important. So the industry has to keep on inventing the various products as per the requirement. Industry has harnessed. We are just working on strings of zeros and one. All the chips which are which work, they use as an input. There is a signal which is transferred, which is converted to a string of zeros, one, and we operate on that. We store these and we do some operations, and based on that, we will make some decision. And this is how effectively the zero and ones have been used. Now the lot of data, if you see, is being generated nowadays. On Google, there is some information that in the year 2023, the amount of data which was generated, that was in a single year, was much more than the total generated in the last 100 years even, and it is increasing exponentially. And lot of data is being created, and where it is created, like there are IoT devices. We have a concept of smart cities. A lot of cameras are being put in cities, so they are connected to some server, they are generating data. Each flight, when takes off, there is a computer recording data and things like that. So huge amount of data is being generated. So once the data is generated, the data has to be stored, and storage should be, any technology has to be economically viable. So the data storage has to be very, very economical, and huge amount of data we should be able to store. So a lot of groups are working on different type of memories. We have seen the evolution of the flash. Our pen drive started with a very small sizes. Now 64 GB, 128 GB pen drive costing 600, 700,000 rupees are available, and see the size. See, the chip is very, very small. Access time is very, very fast. And then comes the data has to be transmitted to the server or to the computer, which may not be at the site. It may be several thousands miles away. So, and that transmission has to be without any wire, or it has to be a wireless transmission. And that's why the fight for 5G, 6G, 7G kind of thing. So data is huge, and data has to be transmitted from one point to another. So we need devices there. And then of course the data has to be processed in big data centers and servers. So in this, there is a concept of edge computing. Edge computing, like a very good example is a driverless car. If a driverless car is moving at a speed of 100 kilometers, there are various devices connected, various radars are there, lidars are there, cameras are there on the side, on the front, on the back, which are taking a lot of data. And the car is moving ahead at a very high speed. So all these devices are giving data, which is basically zero and ones. And all these devices give data in different formats. It's unstructured data. It's not a structured data. Whatever programming we are doing, C, Fortran and things like that, that works on a structured data and it's a structured programming. But here is a case where the data is coming from numerous devices, which is highly unstructured. So what do we do with this? And so, but this data has to be processed. That's where the artificial AI algorithms are important, and AI is taking a lead in processing that data. If suddenly some object comes in front of the car has to decide. If it is just 100 200 feet in front of the car, some object has come and the car is moving at 100 kilometer. So based on this data, the car has to decide whether to stop, take a turn, or whatever decision it has to be taken. So the data is created, the data has to be stored at the edge within the car, the data has to be processed within the car. We cannot send the data to the cloud because of latency issues. We have to make a decision in a time which will be in millisecond kind of thing. So that is the importance. And so if the data has to be stored in the car, we need very, very cost effective memories, very, very cost effective processors, because the whole thing is moving, and it has to be a wired, it will not be a wired, it has to be a wireless data transmission and very, very fast processing of the data. And based on that, the decision the computer will take and convey to the car. So that is known as edge computing. So there are a lot of you can say groups which are working on designing processor for different applications. And now these three things, they are basically generating a lot of data. One is industry 4.0. We have factories where the machines talk to each other, particularly where chips are made. There is not even a single person in the factory. And the machines, they are intelligent. They are generating this data. If there is an issue, then only engineers are sitting outside. If there is an alarm, then they go and fix that. Autonomous driving like drones and things like that, and they also generate a lot of data. And our phone is connected, so many phones are connected on the net, so they are also generating a lot of data. So we are processing data, and the semiconductor industry helps in that. So this is one example I've taken from the Google. Today, modern automobiles, it has a lot of electronics. Around 20%, 30% of the vehicle cost is made of electronics nowadays. And this is an example of the latest iPhone where numerous chips are there. And the reason is we want to add more and more functionality in the phone. We have a TV, we have a camera, we have a radio, we have a computer, we have besides the telephone. So a lot of functionality we are able to add because of the technology, because of the design, because of the sizes of the transistor, which have become very small. Now a little bit of the global semiconductor market, the data which is available 2 years back data. So last year, 2024 semiconductor chips, the components was around $620 billion US dollar, the total market. Out of this, the chip manufacturing is dominated by Taiwan. Close to 70% of these chips are made in Taiwan. USA is 9%, China picking up 7.4%, South Korea 7.4%, Samsung is the leader, Israel 2%, Belgium 1%, and India is not even 0.1% because we have only one foundry, SCL, and it's not a commercial foundry. Our capacity is 1,000 wafer starts per month. 1,000 wafer starts per month, 8-inch wafers. And if I give you these figures of a TSMC, which does around more than 50% of the world production, they are processing 14 million wafers, 14 million wafer starts per month. So this is their production level, and we are at 1,000 wafers. So this is the thing which the difference. And if you see the market share worldwide based on foundry, global foundry is having 52%. Taiwan is 70%, and there is another Taiwanese company which is UMC, PSMC. They account for 16-17. So total chip manufacturing in Taiwan is around 70%, and half of it is by TSMC, which is around 52%. TSMC is Taiwan Semiconductor Manufacturing Company. Then Global Foundry is American. They are around 6-7%. Samsung is also a very big player. They have it's an IDM also. It's a foundry also. So that also is in double digit. So at present, Taiwan is leading in that, and TSMC in foundry business only. They don't design products. They offer their plant for fabrication. Now a little bit about the technology part. You see, most of these chips, around more than 90% of these chips are made from silicon. There are chips based on some other semiconductor material also, like gallium arsenide, which is a compound semiconductor. All GaN is there. All our white bulbs, LED bulbs, they are made from white LED bulbs. They are made from all GaN, from compound semiconductors. But these processors and memories, the semiconductor chips, mainly they are made, which are ICs, integrated circuits, having millions and billions of transistors. They are based on silicon, and the unit, there are many different type of transistors, but the transistors used in making these chips are the MOSFETs. And this is the structure of the MOSFET. And it, as we can see, it has two metallurgical junctions, which we call it source and drain, and there's a gate and there's an oxide. So this is the channel. So it started with 5-micron channel length, and now at present the channel length is, you can say, the technology they call it is 5 nanometer, but that doesn't mean the channel length is 5 nanometer. But it started with 5-micron, and we have come to 5 nanometer dimensions in 40 years. And what has happened is, as you can see, the area of the transistor has fallen drastically down, and the price of the transistor, the dollar per transistor, also has fallen. The cost of processing per square is, it has increased, but in that square we have more number of transistors. That is why the price per transistor has fallen. The devices have become very complicated, very complex, and when we started with the big structures like 5 micron or 1 micron, 0.8 micron, as I told, there were only 15-20 elements in the periodic table. Processes were simple. There were close to 300 or 400 process steps to make these chips. But now, when we reach the geometries which are below 20 nanometer, there are, you can say, more than 50% of the elements in the periodic table. Numerous gases and other chemicals are used in making these chips. Their dimensions have become the geometries have become very small, and a lot of physics happens in this particular area. So the engineering becomes very complex, but we have those models, and we are able to know the behavior of the chip, and we are able to design circuits using billions of these devices. So these are the technology part, and I will not dwell more on this. And basically 90 nanometer, 65 nanometer, 45 nanometer basically is this channel length, the length of the channel. If where the electrons will flow from source to drain, and if the channel length is small, the electrons will take less time and it will have more speed. That is the very simple way of saying. So we started with 5 micron, 3 micron, 2 micron, and like that. And now we have below 20 nanometer, we have below 10 nanometer kind of channel lengths are there. And the structure also has changed. That is very important. It was a planar structure, and after planar structures came the, you can say, till 2011 we have the planar FETs. Then in 2011 2012 we have the FinFET, where we can see the number of fins were there. It had 3 generations of FinFET, and now in 2023-24 it's a gate all around FET kind of devices. And next generation of devices people are working has to be complementary FET, And like you can see here in a CMOS, there is a NMOS device, there is a PMOS device, and here NMOS and PMOS are sitting laterally in one dimension. But here we are putting we are putting NMOS on top of PMOS, and it's a vertical integration. Like in cities, we have uh, many floor towers kind of thing. So to have more component density in a given area, we want to increase the density of the components, and that is the reason. So people are working on CFETs. Maybe in the next 10 years, we will see these kind of devices. Now, as I told you, the material science is very important. So this is how it's a very brief slide. It gives an information like how in each year with the transfer of technology from one node to another, new materials were added. And the reason was once we shrink this channel length, there are severe short channel effects, and there are around 6 or 7 short channel effects. And to counter those effects, we have to change the structure, we have to change the material, we have to bring in new materials. Similarly, at the gate stack, earlier it was a silicon dioxide and a polysilicon on that, and now we have to put in more material, maybe a hafnium oxide, and we cannot deposit hafnium oxide over silicon, so there has to be silicon nitride in between. And then on hafnium oxide, I cannot put aluminum or a copper. So there has to be some other metal on top of it. So that is how the new materials are being added once we change the geometry of these devices. So this is a very interesting thing. And to give you an idea of the design cost, at 65 nanometer, the design cost was around $28 million. At 40 nanometer, it is 37 million. And from 40 nanometer to 20 nanometer, 70 million. 16 nanometer, 106 million. 10 nanometer, 174 million. 7 nanometer, 297 million. And 5 nanometer, the design cost, as you can see, is close to 500 million dollars. So this is the cost of designing a new chip, and this cost involves the cost of the EDA tools, cost of engineer, cost of validation, cost of prototyping. Software means the EDA tools which are used in the physical part and verification and all that. So the cost is exorbitant, and that is the reason these lower nodes are basically used for those products which have a volume, which have huge volume. Then only you are able to make those products commercially viable. This is an example to show that was one MOS device, one transistor. So when we reduce this, so you are seeing a lot of here colors and different type of, so this means the structure is different here, what we call it a well engineering. So in this small area, which will be few nanometer by few nanometer, we have to put various atoms selectively at fixed positions. We have to put these atoms, then only this thing will work. And it's a basically less than 30 nanometer kind of dimension in XYZ. So that's how the processing of these, because we are adding materials, we are adding new materials, and we are doing etching, and we are putting some film, depositing some film. It's all a chemical reaction involved in this, in making these transistors. So the point what I mean is that transistor is becoming very complicated, and this single transistor is complicated, and this billions of these transistors are used in a chip where there are various sub-blocks having different colors. So this means the chip size may be around 16 by 16 millimeter, one side may be 16 millimeter. So there are a lot of different types of memory, different type of processor, various ADCs, various DSPs, glue logic, encryption engine. So you can see that there are so many different blocks, and basically nowadays the design teams, there are 100 plus engineers working on each block. There will be 3-4 engineers, and there will be one chip architect who will be coordinating the integration of all these. So 120 engineer project for 2 years in designing of these chips. This is a very interesting slide, particularly for India, when we want to start semiconductor manufacturing. At what node we should start? You see, these different colors shows the market revenue at each node. And let's start with 2017 and 2018. we see the lower, that light brown color is increasing rapidly. And this color is below 10 nanometer kind of thing. So from 2018, 2019, the below 10 nanometer devices, they are increasing rapidly. The market for those are increasing rapidly, but this we call is the latest node. But the other old nodes or the mature nodes, their market is not shrinking. It is remaining the same. So this, the top one is 180, 130 kind of nanometer market. So that the top 2, 3 colors, if you see, they are remaining the same. So this means the market is being added of the new latest technology is increasing, but it is not affecting the market of the old technology nodes. And if we see 280, like at SCL, we have a 180 nanometer node, and EMS Austrian Microsystems. It's a EMS is a company which is in Austria. Like it's also a PSU. It's a government company. They are working only on 350 and 180 nanometer. They have 3 fabs, and they are doing $2.3 billion business in Europe. Most of the European auto makers, they are taking their chips from there. So they are not into this lower technology nodes. And the reason is, this slide is also again very good slide. At 130 nanometer node, there are 25 companies who have manufacturing plants, who have fabs for at 130 nanometer nodes. These are like companies like Sharp, Cypress, Sony, Infineon, TI, Toshiba, Freescale. SMIC is a Chinese company. Then Fujitsu is again a Japanese company. Panasonic is a Japanese. UMC is Taiwanese. ST Micro is European. IBM is American. Like this. Intel is again American. TSMC, of course, is Taiwan. So at 90 nanometer, now only 18 companies have. 65 and 45, no, not much change in the machinery. So there are 13 players, 13 companies who are having their manufacturing plants at 45 nanometer. 32 nanometer, only 9. 22 nanometer, only 6 are left. SMIC is Chinese, IBM Japanese, Global IBM American, Global Foundries American, Intel American, TSMC Taiwan, Samsung South Korea. Then 16, 14 nanometer node, there are 5 only. And below 14 nanometer, which we call it below 10 nanometer, there are only 3 companies. Intel, which is American, TSMC Taiwanese, and Samsung. Only 3 players, they have this technology below 10 nanometer, and this is basically used primarily for memories and for processors. Processors used in mobile phones, laptop, and server, and things like that. So below 10 nanometer, only 3 players, they call themselves big guys club. A 3 nanometer will cost a product development below 10 nanometer. If you have to develop the technology, only the technology, it will cost around 4 to 5 billion in process development cost. And the plant, which is a fabrication plant, if you have to make a plant of 40,000 wafers, wafer starts per month, below 10 nanometer, you can say geometries, the plant will cost around 15 to 20 billion dollars. And the technology cost is itself 4 to 5 billion dollars. So that is the reason no company can afford it. And to get a reasonably good yield, it's not that easy to have these kind of plants. So now a brief about the status in India. I need not spend much time. All of us are aware of our requirement of the various devices. There is some lot of devices in communication, in power, metering, strategic needs, and they are used in India. At present, all of these semiconductor chips, they are imported. There is some information on the MIghty website, what we will be needing by 64 billion devices by 2026 and 110 billion devices by 2030. And in the next 2-3 years, they say that our import of these devices will be more than the crude petroleum import. And we will need 26 billion in wireless communication, consumer, automotive, computers, wireless, and these are the different heads where we need. And presently, we are importing all these components from abroad, and we are not able to do that. So if we have to start making these, you see, these, if you see in 2030, the requirement is $100 billion. And if you see the different colors and smartphones, it's very difficult to design and fabricate and make the chips for smartphone. It's not that easy for India to start with in the smartphone and servers, because the Intel, there's nobody, no other company has been able to beat Intel for making processor which are being used in laptops and things. And you all know about AMD, how it lost to Intel. So we can start with consumer electronics and automotive, where we don't need uh, transistor which are of low channel length, but higher channel length will do, and the complexities are not that high, and where we can able to manage. So another people ask, why do we need to have the manufacturing base within India? We can have design, we can send design to the foundries abroad, and they can give us the chip. That is perfectly fine, but these are some of the issues. And during COVID times, there were disruption in the supply chain, and and there are certain security concerns, like if we have to use a processor in a missile or in an atomic plant, or you have to use a modem at a PM's house or a president house, or modem, or these kind of RF kind of devices. At present, all of these devices are made from China, so there can be some risks. And recently, we had some skirmishes 3 4 months back. We were using drones. All the electronic which are used in these drones, they are basically made in Taiwan or China, but we have no option presently. But there are risks involved in those things, and that is the reason the government is trying to encourage and add a lot of semiconductor manufacturing in India. And they have government has come out with a semiconductor policy, 80,000 crore, 10 billion US dollar will be they have earmarked for that. And these are the various I will come to various schemes which the government is in the semiconductor policy of 2021. The government will subsidize around 50% of the fab cost, capex, as capex only. If any companies is willing to set up a fab for any technology node, and display fab, compound semiconductor fab, photonics fab, sensors fab, 50% of the subsidy will be given by the central government. And there are various state governments like Gujarat and Maharashtra, Andhra, Telangana, 20% they are giving. So total 70% of the project cost is being funded by the government. Besides this, there are three other schemes: production linked incentive, design linked incentive, and C2S, which is basically for academia. More than 125 different universities, they have been given huge grant, and they have been given tools, they have been given manpower. Uh, they can recruit research staff and develop certain chips for that. And these are the plants which have been cleared so far. Tata Fab has been cleared, and the Tata Fab project was cleared around 2 years back. Civil works is in progress. They are a TOT. They have a TOT technology transfer from PSMC Taiwan. PSMC is not in the top 5 or 6 semiconductor companies, but the PSMC was only the top 5. They never shown any interest in investing or in India directly, or giving their TOT to any Indian company. So BSMC was willing to give, and that's how we have entered into a collaboration. And Tata is putting a fab in Dholera, Gujarat, and they are saying they will start with 110 nanometer, and the total cost is close to 80 or 90,000 crore, and this will be spent in the next 4 or 5 years. The total fab capacity is planned to be 50,000 wafer starts per month, but it will take around 5-6 years. And then there are a lot of assembly and packaging units which have come, and Micron, CG Power, Kenis, and RRP Electronics. So these four companies, they have put the assembly and test where the investments are not as high as in setting a fab. And I just want to show you, if I want to show you one wafer, which is a silicon wafer, and standard. You see, these fabs, they will start with these wafer. It's a unprocessed wafer. If you are able to see this phase, this is the front side, and this is mirror polished, and all processing is done in this side. And it's a 8-inch, around 625 micron thick. These are standard wafers. If you are able to see, I don't know if you are able to clearly see this. And this is one processed wafer where you can see a lot of dies. And in this, if you are able to see some small squares, small rectangles, small polygons, so these are the dies, these are the chips which are made, and is the same after processing. So these are some of the things, some of the projects which have been started by the government, and this is the location. Most of these products are near Ahmedabad, and these are the various academia institutions which have been given a lot of funds, EDA tools and manpower to learn design, and there are close to 125 educational institutes, all IITs, NITs, and things like that. Now, the basically skills required, you see, in this industry, in semiconductor, all the processing, it's basically, we are using a lot of gases, chemicals. It's basically a chemical reaction. So if you are if a person is involved in this, he has to know a little bit of everything about the thermodynamics, about the material science, and the physics, and those are basic, because now when the device structures are very small, there are quantum effects. We have to calculate the current and how much current will flow, and that you have to calculate how much electrons are there in the valence shell, how much electrons are there in the conduction band, and how they move, the transport phenomena, basically the quantum part of that. And that is the behavior, and you have to transfer that behavior into mathematical equations, which we call it models, which can be used by the circuit designers. So to be in this particular industry, these are some of the courses which are required. These are all standard courses. I think our educational institutions like the top IITs and NITs, they have a very good curriculum. They are teaching all these courses. There's nothing great about this. And but only thing is, there are very few universities where where a student can learn all these concepts. Otherwise, a lot of mushrooming of various universities where even the talented faculty is also not there. So if I summarize the semiconductor scenario in India at present, there is no complete line of manufacturing. We are doing some assembly of various phones where the value addition is only 10-20%. Wafer fab, as per industry standard, we have only one wafer fab where we have a class 1 clean room, which is SCL. There are 2-3 prototyping fabs at IIT Bombay, IISc, IIT Madras, IIT Kharagpur, but they are prototyping fab. There you cannot make a transistor or a chip, but you can deposit some film, you can pattern some film, and do some proof of concept kind of thing. There are MEMS fabs also where we can do MEMS sensor at Siri Pilani and DRDO Sitar, which is in Hyderabad. And GATEC is also there, where we can do gallium arsenide RF transistors, basically. So the presently one commercial high volume manufacturing fab is in progress, which is by Tata, and 4 unit of ATMP, which we call it the testing and packaging units, are also being cleared by the government. And there, I think ATMP units, their civil works are almost complete. By next year, they will start working. There is a lot of scope for solar cells also, and a lot of scope for gallium nitride devices also. There, the capex requirement is not as high as used as required in CMOS fab, which is close to 70,000, 80,000 crore. But for a GaN or a silicon carbide fab or a solar cell fab, it's not that high. It is 3,000, 4,000 crore. But the technology, only three, four companies in the world that only they have the technology part. And so there is a focus on those kind of fabs also. And maybe in the next 2, 3 years, we will see some more units coming up in that particular area also. So a little bit, I think I will take 5-10 minutes more. This particular semiconductor manufacturing, if we see, there are various verticals. One is the process technology. The process engineer, basically, they will design the process. They will design the components, basically. The components can be active and passive, like transistor, R, L, C. So they will design the process. The process means by how these transistor RLC will be made. What will be the models of these? What are the process steps? Like if I give you an example of our thing, 180 node, there are close to 720 process steps, and each step involves addition of some film or removal of some film or patterning of a film. So for each step, there is a particular step unit recipe, like what is the gas used, what is the flow rate, what is the temperature, what is the pressure, and things like that, So the process engineers, they should have a good knowledge of these thermodynamics, material science, electrical engineering, chemistry, computer science, a little bit of everything. And they are highly demanded in the industry because it involves a lot of knowledge of various other things, and one has to work on the machine. There are software tools available which we call it a TCAD, but it's not that like you can say 99.99% accurate. A lot of things have to be learned on the machine itself. And then they are VLSI designers, circuit designers. Circuit designer means they will design circuits using these components. They will not design the components. They will use these components as a black box, and they will design big, big circuits. There are different types of circuit designers: digital, analog, RF, mixed signal, data converters, and things like that. So huge requirement of uh, design engineers are there already in the world. I think in uh, Bangalore and Hyderabad, we are having close to 20% or 25% of the total world's design engineers based here. All companies, big, big companies, starting from Intel, Texas Instrument, Analog Devices. They have huge number of design engineers. Intel is having around 9,000 or 10,000. Samsung is having around 9,000, 10,000 design engineers. So they are designing circuits. And then there are people who work in fab. They will process those batches. And then there are people who will, fab needs a lot of, around more than 300 different gases and chemicals. So there are people, and those gases and chemicals, particularly, there are bulk gases which are required in high volume. And you have to make a plant there itself. Like in SCL, we have a nitrogen plant, we have a hydrogen plant, and you need people who can run those plants. And the requirement of these gases and chemicals are very, very critical. They are very, very pure things are needed. I will show you some of these things because the time is running. Now I will skip some of these things. This is a few of the designs which we did in SCL. They are being used in the rockets and satellites. And I don't have the time to explain about these designs. And now the important, just please see this a clean room. So these are a very brief clip of TSMC, which accounts for 70% of the world's production. I want to show you some of these slides because these are all process and it requires a lot of time to explain. You see, this is the uh, challenges at when we make ICs which have geometries below 20 nanometer. This is the size of the wafer, which is a 12-inch wafer. 12-inch means 300 millimeter size. A 20 nanometer particle, if it is sitting on the wafer, it can affect the yield because we are printing structures which are below 10 nanometer. So from where the particle will come? The particle can come from the gases. It can come from the chamber itself. It can come from the human if they are there inside the fab. Normally, there are no people inside the fab. So it can come from the gas, from the gases if their purity level is not as high as required. So we have to detect that after each step. Like in 180, there are 600 steps. After each step, you have to do the physical inspection, whether that process is whatever step was supposed to be done in that step, whether it is done or not. And another thing is the washing. There are three levels of wafer cleaning. And after the cleaning, we have to ensure that the surface of the wafer is clean. There is no particle sitting. There is no deposit of any chemical there. So to find this 20 nanometer particle in an area of 300 millimeter wafer size, this problem is same as locating a coin between two cities on a highway which are around 300 kilometer apart. A coin diameter may be 1 inch, 2 inch you can take. So 2 inch divided by 300 kilometer is the same as 20 nanometer divided by 300 millimeter. But they are able to do. TSMC is able to do these things, and that's why their yields are very good. And it is only Intel is not. Intel yields are very poor, 10%, 15% at below 10 nanometer. So even the Intel for their processor, they are going to TSMC. So this is the perfection that TSMC has done. Another thing, you see, there is a step where is it's a chemical mechanical planarization step. And we, after depositing a film, after etching, there will be some roughness, and we want to planarize the surface. And that surface has to be plane, uniform, within 10 angstrom thickness, uniformity, 10 angstrom in 300 millimeter wafer dia. So this is same as if we have a 400 meter running track, we need a flatness control to the thickness of few papers. So these problems are same. So they are able to, TSMC is able to do all these things, which are like they have these equipments which by which they are able to do this. Now to give you an idea of the various gases, these are the bulk gases, like they require in huge quantity. And see here, their whatever we call it, the purity level, it's in ppb, ppt kind of thing, and it has to be very controlled. And you have to make these nitrogen, oxygen, hydrogen, argon, helium, they require in huge volumes, and you have to make a plant there itself along with the fab. And through these stainless pipes, these chemicals will go to the fab. And these you can say the pipes, they are SS316L, which are all imported from US. It's not made in India. Most of these chemicals are imported from US. They are not like made in India because we don't have any much requirement of these things. So these are some of the, now the water, it requires ultra pure water, and ultra pure water is just H2O. And the test is the resistivity. It has to be a 18.2 mega ohm centimeter. And there are, you can see a big UPA plant, ultra pure water plant. And there are a lot of tests for that. And you can see TOC analyzer, particle counter, silica analyzer. There are 10 different types of tests for testing that water itself, that it's a pure water. And nitrogen plant, pure nitrogen, and things like that. So this is the, and then there are certain gases which are various chemicals like these acids, hydrofluoric acid, nitric, phosphorus, all these chemicals are required in the processing. And silane, trichlorosilane, dichlorosilane, arsine, phosphine, diborane, these are very, very hazardous chemicals. And the engineers have to play with these chemicals. There are certified people who only can touch these cylinders. They are specialized gases. They, there are bunkers where these cylinders are kept, and through piping and through safety mechanism, they will go to the chambers where they are used for different processing. All these fluorinated compounds. So in a periodic table, almost more than 50% of these elements have been studied, and most of these elements have been used in making these devices. Then huge amount of power is needed. Then your droops, which is a rotatory UPS, is needed. DG sets are needed. Then the process cooling water, compressed dry air, vacuum, exhaust, and things like that. And you need, of course, good manpower and things. Then there is a safety mechanism. There is a 3 level of safety is there. Leak detection systems are there. And then waste management is a big issue. Our fab is not, because we are using 1,000 wafers per month. But the big fabs which are having millions of wafer starts per month, so they will be using huge amount of these chemicals. And these to finally, after the process, so all these toxic wastes have to be treated and before disposal. So that also itself another big area. And then these are some of the assembly and testing, some of the testers which are used in testing of these wafers, testing of these ICs. So in India, we have 4 plants which are only for testing and assembly of these ICs. And you can see these probe cards and these things. This is a structure of the die, which basically it's a voltage regulator used in the chip. And this is a metal, it's a aluminum, the dark brown color which is being shown. This is a transistor, this is a MOS, and a lot of metal is being put. So these are some of the dies. Just I want to show you the picture. So this is the wafer picture, and this is one die out of it. And these are the processors. This is a 32-bit processor Vikram, which is designed by us and fabricated by SCL. And this is the processor which is used in rockets. All our space launch vehicles, they use this kind of device. It's a radiation hardened. It doesn't have any effect on. In space, there is a lot of radiations, so this chip is not immune to that. Is immune to that. So these are the various products which were developed by SCL. Being SCL was mainly for strategic requirements, and it's not a commercial fab. And the requirement of space, military, around 70% of the requirement of this can be is not on the low geometry. There is a technical reasons for that. We will need a technology, need the devices which are very rugged, which have a very high level of, you can say, there should not be any failure rate, high level of reliability. And we work at voltages which are more than 5 volt, 10 volt. Whereas these lower geometry devices, they work on basically VDDs which are less than 1 volt, 800 millivolt, 700 millivolt, where the noise margins are very, very less. So we will never use, nobody will use these kind of devices in a military or a space applications. So for a military or a space or atomic energy applications, we don't need the latest technology. All those mature nodes are used to design these circuits. And these are some of the circuits which were developed by SCL, and they are being used. And for making a product a military or a space grade, there is a big procedure for screening and qualification. Various types of chambers are used, where we give a lot of shock, like thermal shock, air to air, liquid to liquid. We do the vibration test. We will subject the device to very high acceleration, 10,000, 4,000 G acceleration or 10,000 G acceleration, and the package should not break, and the wires, the bonds should not break. So, and the various other, we also subject the device to a mechanical shock, 1500 G. So these kind of tests are done, and then only the devices are put in a rocket or a missile. So all those kind of infrastructure in terms of various chambers and various equipments, they are available at SCL. And this is what for this, I mean. So I think I will stop here and I will take a few questions if you have any. So my I in 1 year I can only give a broad outlook of a bird's eye view of the whole thing, because it's a very interesting area and a very interesting field, and for the youngsters particularly, lot of good career scopes in this. Only thing is, one, they have to focus on their whatever subjects, whatever syllabus is there in their BTech electronics. So that only is required, nothing extra, nothing great is required in that. So any questions, I will be happy to take.
So thank you, sir, for giving a comprehensive overview of the chip design and manufacturing space. We will open the floor for any questions from the participants.
May I ask a question?
Yeah,
Professor Jattani, this is a
Sam, just a
wonderful.
second. I just want to thank him because I have to leave for a meeting. Thank you very much for a lovely lecture. Maybe you can come and give more detailed lecture on semiconductor manufacturing at some point. Thank you. Sorry, I have to
Thank
leave.
you, sir. Thank you, sir. Thank you.
Good evening, Professor. I am Dr. Vijay Kumar from Shri Ishwar College of Engineering, Coimbatore.
Just 1 second, you can ask, but Sham, can you go ahead? And after that, you can Vijay Kumar, you can ask.
Okay. Thank you, Dr. Jattani. It's a wonderful opportunity for us who don't know to get a bird's eye view of the whole field and and the current status of this in India. My question is about the historical angle on this. I believe India had gotten a rather early start, if not earlier start a few decades ago on this semiconductor manufacturing, which came to an end with the fire in Chandigarh plant. Would you enlighten us about that event and what happened and what was done after that? Did we just give up or what happened?
True. Sir, we started in 83. The first batch came out from SCL in 1983. That time it was 5 micron CMOS. We had a technology transfer from AMI, American Microsystem Incorporates. That was a very big company. Two companies were started at the same time. One was SCL, another was AMS Austria. So that was Austrian Microsystem with the same technology transfer there and here. The idea was a team of around 20 people stayed there for 2 years in US plant from 1981 to 83. And the idea was we will learn this technology and the further developments we will do in-house. We were doing in-house also. From 5 micron, we developed 3 micron, we developed 2.7 micron, we developed the process, we developed a lot of designs also. But in 1989, there was a fire in the fab. The whole plant was burnt. And when the plant was burnt, it was an accident. But it took 2-3 years of CBI inquiry, and then the common procedures. They took around 7-8 years to rebuild that plant. But in that 7-8 years, many people left. By that time, there were a lot of opportunities in Singapore, in US, of basically process engineers. So the world was shifting every 1.5 year. They were going to the lower node, but we were not able to do that. We were doing some chips for the military that time. And in 1989-90, they told we want those chips because it was a telephone exchange for the army. Army, as you know, they have their own telephone exchange. They don't use BSNL, or that time it was a DOT. So there were 9 chips for that, which we were calling a plain errand circuits. So they told you, we need this, you do whatever you like. Wherever it is available, you do. So then AMS was a similar foundry, similar technology. So we hired their plant for doing this. But the defense told that you cannot give the design information, design tapes to them. So then around 7-8 of our engineers were stationed there. They were running their batches. We hired their plant equipment for running their batches. The cost was like that only. So we were doing that, but in that process, we were trying to develop the new process also with certain limitations. But 7-8 years was a big thing, and then many people left. They got good opportunities in various other areas. It took a lot of time, and after that, you see, unless the governments highly subsidize this, there we because the investment in a fab is huge. Now, if you have to make a plant, it will cost minimum 40,000 crore. It will take 5 years, 4 5 years to build. Whatever products you make on that plant after 4 years, you don't know whether it will be commercially viable at that price or not. Even now, if you see, the government is offering 70% capex subsidy. The top 3 or 4 players, which are Intel, TSMC, Global Foundries, Tower Jazz even, they all refuse to set up their plant in spite of the government is giving 70% of the subsidy. So because it's a, even the Tata agreed because, and they have worked out that, and the return on investment is in the 9th or 10th year. Despite 70% of the subsidy, the remaining 30% is people are not willing to invest. And it's a highly critical thing, and the process is complex. Very few companies know that. We don't have process engineer as well, and if you have to get the process people from abroad, the salaries are very high. And the good designers, analog designers, there is a shortage of good analog designers. There is a shortage of good RF designers in India. There is a shortage of good digital architects in India also. And all our manpower which are there in the design, basically they are doing verification jobs, and they are doing limited jobs because the main design engineer is sitting in US, and they will give them some sub block, some small area, and they don't know where that particular unit will fit in the complete chip. So the answer to your question is, the government that time, they were not very serious. In mid 95, 97, when smart cards were coming, when energy meters were coming, so SCL and BHEL, Bell, they made a consortium kind of thing. They told, look, we can get some technology, we can put 5 plants, and we can make these smart card here in India. That time it was known that it will have a huge market because everywhere driving license, ID, library card, these smart cards were used. And smart card was not a very great chip. You need only 8-bit processor and some memory that time. And memory and both volatile and non-volatile memory, it was easily doable. And only thing is, it was not possible to meet the price which those MNCs were able to do that. And these government PSUs, they wanted that you take at least 50% of the total product from us and 50% let it be in the open market. But somehow it didn't materialize. And finally, the ST Micro, that time, it was ST Micro, they flooded the market with smart card very cheap. And the same thing happened with your energy meters. Hearing aid chip were designed at SCL. We designed energy meter, 1 phase, 3 phase, hearing aid chip, single chip telephone, and pacemaker for the heart. Those things were also designed at SCL. They were made, they were fabricated, they were working. But only thing is the price part. It's not possible to meet the price which a MNC can give. And for that reason, it was not successful. The government never backed up. Now the government is giving good subsidies. Even TSMC, if you see their history, government has invested a lot of money there. Even America now, you see, around the world, 28 fabs are coming up. And out of these, around 7, 8 are lower node fabs, like below 10 nanometer fabs, and each fab costs around 80,000, 70,000 to 80,000 crore. 2 of these fabs are coming in US, and US is funding, I think, around 80% or 90%. These fabs are made by TSMC and Intel, and 80% of this is being funded by the US government under a program which they call it CHIPS, CHIPS. So unless the government funds in a huge way, then only we will be able to, any company will be able to survive. That never happened. And now it's a good beginning. Let's see in the next 3-4 years. I guess huge number of jobs will be required. Lot of good people are required in various categories in this particular area.
Thank you.
Dr. Vijay Kumar.
Yeah, good evening all. And Thanks, Jattana sir, for the nice session. So it covered all the market segments where the semiconductors plays a major role, as well as the fab part, which is going at the back end. So this will be very useful for students
Can you focus on your question, please?
so just I want to thank sir for the nice session and
Okay.
giving
Yeah,
us an
okay.
opportunity to attend the session.
Thank
Thank
you.
you
So
all.
there is a question on the
Thank you.
chat.
Thank you, sir.
Yeah, there is a question on the chat. I'll just read it out from Manash Pratim Sharma. The first question is, what are the key factors that will influence the development of a complete semiconductor ecosystem in India? Second question is, what are the prospects of non-silicon based devices and systems in the coming years?
Sir, the first question all depends on the success of the Tata Fab. Once the Tata Fab runs full throttle, 40,000 or 50,000, so a lot of the ecosystem will naturally develop because there is a whole supply chain will only come when their production level peaks at around 50,000 wafer starts per month. Then there will be companies who will be interested in making these gases at those purity levels, and new fabs will come. So all eyes are on Tata Fab, and I think it will take around 3-4 years for them to stabilize their production and to stabilize the yield, particularly 90%, 95% yield have to be maintained at any cost. Then only it will be commercially viable. Next is your question is related to compound semiconductor like gallium nitride, silicon carbide, and other solar cell fabs. There, the investment level is not very high, not more than 5,000, 7,000 crore kind of thing. But still, no project, nobody has come forward to make those fabs. Though there is a huge potential in terms of GaN silicon carbide for electric vehicles or electric buses, electric lot of these things they work at 80 volt 120 volt batteries. Silicon is not very good. Silicon transistor at more than 100 volt it's not very efficient because of the Aron kind of thing. So silicon carbide and gallium nitride, they are better and they can go up to kilowatt and megawatt kind of power. It's very small chip, can handle kilowatt and megawatt kind of power. But again, nobody is coming because the technology again is only with three or four companies in the world. They may not be willing to part with the technology. They can sell you the product, but they may not give you the details of the technology. So these are highly, you can say, highly high-tech areas. Though the structures there, they are not in nanometer, they are in microns. Number of transistors are not more. There are only 2 or 3 transistors there. So that is a different, but then it's a basically hemmed kind of devices. There are various layers depositing and very, very fine layers we are depositing. There is stack of layers like aluminum nitrate, you start, then gallium nitrate, then aluminum nitrate. So various layers are there. Each layer may be of 5 nanometer, 4 nanometer. So all those technology is not that easy to develop. We don't have that. And there are very few companies, and unless I hope that some of these fabs will come. Many people are working, they are trying to set up those fabs because capex requirement is not that high and the structures are not very low geometry structures. They are in more than 1 micron. Process steps are also not very high there. Basically solar cells, they are PN junction, they are PN devices only. The process steps are not more, it's less than 100. Whereas in a below 10 nanometer process, the process steps are more than 2000. And each process is very, very complicated. We are dealing with line widths which are in nanometer, 10 nanometer to 5 nanometer kind of thing. Here it's in microns. So all those things are there, but still there is no breakthrough. But I hope in the next, people are waiting for Tata Fab. This is what I feel. Once their fab starts running in 2027 and 28, the other fabs are likely to come.
Good evening,
Any
sir.
other?
May I ask
Yeah.
a question?
Yes, please.
Good evening, Jattana, sir. Rajivan here from NIT Hamirpur. It was
Evening.
wonderful to hear you, sir. Like in SCL Mohali, presently we have 180 nanometer fab lab. Are we expecting it to be upgraded to some other technology in the time to come?
Yeah,
Because there
madam.
is incentive. There's a lot of incentive from government for SCL
Yes.
also.
Yes, right now there is a tender of 4,000 crore, and there they are expanding the capacity from 1,000 wafer to 2,000 wafer starts per month. And 4,000 crore already tender is there in the last 2-3 months, and they are working on that tender. And that plant, because at 180, the full potential of 180 has not been, we have not been taken full advantage of that particular node. So that plant will work as it is. Besides, I think the government has earmarked 10,000 crore for maybe a 65 nanometer or a 90 nanometer technology, a separate fab for that. This will not be disturbed. So 180 will go, and a separate 65 or 90, it's not decided. And that plant will again will come up, and I think 10,000 crore has been earmarked for that. In 10,000 crore, you can get a 90 nanometer, some 2,000, 3,000 wafer start per month plant with a limited commercial. And moreover, the government intent is to use SCL as an R&D fab and a fab for academia also. SCL is willing to fabricate any chips designed by any educational institutions free. MIT is funding that. I think they have already given 24, 25 devices this year. When I was there, we fabricated more than 80 devices. So they are doing this, and it's a good opportunity for academia, and to use that, to learn that design, to get it fabricated from SCL, test that chip when it comes, so that they know the entire cycle from the specification to the silicon.
Right, sir. Thank you very much.
Thank you, madam.
Yeah, we will take one last question. If anyone has any question, please go ahead.
Yeah, actually, I joined late, so I'm Professor Shivde from IIIT Jabalpur. I just would like to ask, because we were working with some cooling technology, so can we somehow get the details about the heating zones? As you are saying, these are the thousands of transistors which were installed. So with reference to a chip used for a particular purpose, how these heating zones are created? Can we get some sample information?
Yeah, madam, I guess you want to know the details of the heating zone within the chip.
Within the chip, yes. Within the chip of whatever size you are saying.
I got your thing. I got in the design flow. If you are using a digital or an analog flow, in the design flow, you can measure the current at the various nodes, which is flowing. And because it's basically in the chip, it's a I square R heating. On the nets, what we call it, the connects, it will have some resistance, and I square R heating will create the increase in temperature. And those things, based on the temperature, that map the software tool will show you the map in that. In a colored thing, that will know. If you have a IC, like if you are using a Synopsys design flow, then after a design compiler, if you use the layout using ICC, then there are various options in that, where you can see the voltage drop, where you can see the current flowing in each, and where you can see the temperature also. How that, and in fact, the designer is supposed to do all these things, because if there are temperature zones in that circuit, whatever transistors are sitting close to that area where temperatures is high, their VT will change. Their VT will get affected. If temperature is more, the VT will also fall, and that circuit may misbehave. So all those things, the designer layout, it has to be done carefully, so that he is able to manage all these issues. So yes, it is possible to do that using EDA tools.
EDA tools. Okay. Thank you, sir. Thank you very much.
Thank you. So thank you, sir, for taking your time and speaking to us and providing a very broad overview on this entire semiconductor manufacturing in India. And I hope it was useful for most of the participants also here. We will probably have a follow-up call on looking at some of the details, maybe at a future point in time. And the recording of this will be made available on the Cree website in a couple of days. So if anyone has missed out or wants to share this, you can please visit the Cree website and take a look at the talk and also the past talks in that portal. We will have our follow-up talk, the next talk in 2 weeks' time. We are trying to finalize. We will share the details of the talk shortly. So thank you all for joining today. We look forward to your joining in the next talk. Thank you very
Thank
much.
you.
Thank you, sir.
Thank you,
Professor
sir. Thank you.
Jattana, I might
Yes, sir.
mention that this is one of the highest attendance sessions. So there's a very broad interest in your talk. So thank you.
Yes, sir. Sir, actually, semiconductor is a very like a hot cake these days in India. I think for young engineers also there is a lot of good opportunity, and it's basically it's a very interesting area. And maybe if some of the people are interested, we can have a specific talk on how chips are made on the fabrication flow. Like as I told, it's basically a chemistry, and the end result is electrical. So it's very interesting where thermodynamics and all material science, all thing, mathematics, physics, they join together to make such beautiful
Yeah,
products.
maybe that
So it's
perspective,
very interesting.
yeah, the interdisciplinary synthesis, how it is done, maybe you could
Right, sir.
just focus on that. We could have a separate talk on that.
Right, sir.
So actually,
So
Professor Sham is pointing that there should be a follow-up talk soon.
Yes.
yeah, we will coordinate with Jattana sir and arrange for that. Thank you very much. Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you all.